if we have a triangle ABC, any triangle ABC, and now we try to erect equilateral triangles on three sides of it. We try to erect equilateral triangles on three sides of it. So earlier, in the first theorem, we erected triangles whose angles added up to 180 degree. In the second theorem, we created triangles which are similar to each other. In this particular case, all of these triangles are equilateral in nature. This is D, this is E, this is F. So how do you show that the circumcircles of these three equilateral triangles will pass through a single point? The terminal angles would add up to 180 degree. These angles are simply 60 degrees. So we just apply the previous one and we are done. We come to the theorem that we just created. What if we draw the circumcenters of each of these triangles? So let's suppose the circumcenters are O1, or maybe this one is O1, O2, and O3. These are the circumcenters of these three triangles. So what was the hypothesis in this particular theorem? The hypothesis is that these three triangles are similar, right? AFB DCB and AEC are similar. That's what's given to you. That's a given data. So what we have done is we have created a triangle. We have created a triangle with the circumcenters of these three similar triangles. We have created a triangle using the circumcenters of these three similar triangles. So show that O1, O2, O3 is similar to each of these triangles. To AFB, which we know is similar to DBC, which we know is similar to AEC. In the special case where it is equilateral, where each of the triangles are equilateral, then the circumcenters would create an equilateral triangle. And this is called the Napoleon Triangle. Or sort of the outer Napoleon Triangle. There is the inner Napoleon Triangle that we can talk about, but this one is the outer Napoleon Triangle. So this is the crux of the proof that we are trying to achieve, but there are certain caveats to it. So we have to be really careful about what we are doing here. Equilateral triangles on three sides of any triangle ABC. ABC could be scalene. Only the externally erected triangles need to be equilateral. We want to show that the circumcenters, the triangle created by the circumcenters, that triangle is an equilateral triangle. It's quite a claim, actually. Well, we actually want to do more than that. We want to show that we don't even need equilateral. We can generalize it. If the three external triangles are similar, then the triangle created by joining the circumcenters is similar to those external triangles. So this is a very beautiful theorem, and apparently it is attributed to Napoleon Bonaparte. the French emperor. Uh, as far as legend goes, Napoleon was had some flair in mathematics, or he was interested in mathematics. In fact, Napoleon was so much interested in mathematics, when he attacked Germany, he did not. He stayed away from the town of Göttingen, and the reason he stayed out of the town of Göttingen is it was the home for the one of the greatest mathematicians of all time, Carl Friedrich Gauss. So, well, sometimes mathematics can save your lives, I guess. But the thing is this, that though this theorem has been attributed to Napoleon, uh, not many mathematicians actually believe that Napoleon could come up with such sophisticated amount of mathematics. But anyway, we call it Napoleon Triangle for the fun of it. So give it a little thought, and in the meantime, let me remind you what are the tools you will need to show this. So this is a toolbox. You need the notion of radical axis, and this I have discussed sometimes in my in the geometry module of our program. The gist is this, that radical axis of two circles is usually defined like this. So it's a line that is perpendicular to the line joining the centers. It's a line that is perpendicular to the line joining the centers. And moreover, power of any point. So if you draw tangents from the line to these two circles, let's say T1 and T2, then PT1 square equals to PT2 square. So power of a point, power of the points on this line from these two circles are equal. Power of the points on this line to this circles are equal. So if you attended one of those geometry modules, you would remember that power of a point is just a way of thinking about the distance of a point from a circle. The distance of a point from a circle. So PT1 square equals to PT2 square. That precisely is the definition of radical points on the radical axis. There are multiple ways of defining power of point. One way is you draw a tangent from the point to the given circle and take the square of the tangent. The case that we will be using is the following. If we have two circles and if they intersect at 2 points, if you have two circles and if they intersect at 2 points, then the radical axis is simply the line joining the common chord, or the extension of the common chord rather. So this is O1, this is O2. So this is the radical axis. Which is the extension of the common chord. Now you join the centers O1, O2, and you have this A and this one as B. We know that the line joining, so this is something you can use, line joining centers is perpendicular to the radical axis, which is the common chord. Okay, so then what can we say about O1? Okay, maybe I can go back to this picture. What can we say about O? So this point where all of the three circles pass through, this point is called P, suppose. So I'll just clear the clutter a little bit. If this point is P, then we can say that this is O1, O2, O1, O3 is perpendicular to BP. O1, O3 is perpendicular to BP. And let's join AP as well and CP. So let's call this point X. Now what can you say about O2, O3? What can you say about O2, O3? O2, O3 is perpendicular to something. Excellent. O2, O3 is perpendicular to AP. Very nice. Let's call this Y. Now, do you see any cyclic quadrilateral in this picture now? Can you see any cyclic quadrilateral in this picture? PXYO3. Excellent. As Anant pointed out, this is the cyclic quadrilateral that we are looking at. Why? Because we just showed that this angle here at Y is 90 degree and this angle here at X is also 90 degree. Angle X is 90, angle Y is 90. So certainly that quadrilateral is cyclic. Yes, there are three of them of this type. That's correct. Okay, so what can you say about the relationship of angle O3 with angle P facing it? So what can you say about angle O3 and angle P? Well, they are supplementary. That's correct. They are supplementary. So this is 180 degree minus angle P. But there is another angle in this picture which is 180 degree minus angle P. There is another angle in this picture which is 180 degree minus angle P. Okay. Anant has an excellent Anant. Very nice. You see, that is equal to angle red. Okay, so you can see why. Why is that? That is because this is a cyclic circle. This is a circle and angle P is supplementary to the red angle. Angle P is supplementary to the red angle because AP BF is a cyclic quadrilateral. APBF is a cyclic quadrilateral. Excellent. So as Anant rightly realizes that this angle O2 is now similarly equal to this purple, and angle O1 is equal to this green. So the inner triangle is the Napoleon triangle is certainly similar to each of the similar triangles that we have erected earlier. So beautiful proof, because we are using the newly created cyclic quadrilaterals inside. And for the case when we erected equilateral triangles on three sides, we get that the outer Napoleon triangle, this one, O1, O2, O3, is equilateral, because each of these three angles would be equal to 60 degree, which does the trick.